adaptation planning. Bronwyn?
Thank you. I'm going to introduce to you our hazards mapping projects, and the next two presentations by Phil and Tony describe research that contribute to these projects. So I'm going to start by setting the stage, handing the mic over to Phil and Tony, and then I'll come back again to wrap it up and describe how we integrate and communicate the science that we're doing. So I'm from the Northern Climate Exchange, which is part of the Yukon Research Centre. We have a number of programs that run out of the centre. We're the climate change branch, you could say. We've been around since 2000 in different forms, and we've evolved most recently to focus really on adaptation. We also do a lot of work around education and outreach and some work around mitigation. And then the other program that we run through the Northern Climate Exchange is related to climate change information mainstreaming. And this is a program that's funded largely by the Climate Change Secretariat, which is one of the organizers of this conference. And so Alison Perrin, who runs this program, will speak tomorrow. The work that I'm going to describe today, and a presentation that you'll hear from Fabrice Camas tomorrow, describes work that we're doing around adaptation, and specifically around vulnerability assessments and hazards mapping. So to give you a little bit of our context in southern Yukon, we are in the sporadic and extensive discontinuous permafrost zones. So we know we're sitting on a lot of permafrost in a lot of our communities, and we hear that a lot from our community members. You've seen this map from Sharon Smith and colleagues already. I'm using it here to illustrate that in southern Yukon, our permafrost mean annual ground temperatures, our permafrost temperatures are really warm. We're between -2 and 0 degrees. So we're on this warm, really often ice-rich permafrost. And as we know, this means that we need to do careful planning in order to respond and adapt to change in that permafrost. And so that's what gave birth to our hazards mapping projects. We work with a group of folks, as you'll see from Phil and Tony and others in this room and that are not here, to complete these projects. We've done hazards mapping projects in 4 communities so far, in Mayo, Pelly Crossing, Burwash Landing, and Destruction Bay, and we're currently working in Dawson, Faro, and Ross River. And as we were developing the projects and as we carry them out, we're always trying to keep in the forefront of our minds who this work matters to and what we can do to make sure that the work is integrated. So we know that the work matters to the First Nations, the consultants, the engineers, the planners, decision makers, and importantly to the residents of the communities that we're working in. So we're trying to put a lot of energy in ensuring that we're doing meaningful communication and community engagement with these projects. So at the outset, we always seek the support of the communities and First Nations that we're working with as part of our proposals. We hire local community coordinators who act as liaisons between the community and the research team, feeding the community information about the project and then bringing the research team updates about community questions, concerns, looking for ways to integrate. I'll describe how we carry out our projects, but we do choose specific field sites to work in, and we do that in consultation with the community. So we find out from them areas where they're planning future development or where they've seen problems. We look for opportunities to involve schools, to do tours of our field sites. We do a little celebration at the end of the projects that I'll talk about later, and some targeted communication projects. So when we go into communities to bring in these projects, the first question that we get asked is, what are hazards? What do you mean by landscape hazards mapping? And so I want to just talk about that a little bit here because I know that sometimes the definition of hazards mapping or the scope changes depending on the group that's doing the project and the needs of the community. We're looking at 3 different aspects when we're talking about hazards. We're looking at surficial geology, at permafrost, and at hydrology. And we create a fairly simple hazards ranking, a stoplight color-based ranking. In our last projects, we had to introduce an intermediate color because we had so much really interesting permafrost around Burwash and Destruction Bay. And so the idea is that this is easily interpretable and serves as a first step in decision-making around development and permafrost. So using our most recently completed project in Destruction Bay and Burwash Landing as an example, I'll just describe to you how we carry out our projects. We've heard again and again that surficial geology is really the first step in assessing permafrost. So we work with the Yukon Geological Survey to create surficial geology maps in the communities that we're working in. And so that's the yellow outline that you see here. So the YGS does mapping at 1 to 20 or 1 to 25,000, which is new in these communities. Most communities don't have maps at that scale. So that's alone a significant contribution to communities. And then we outline a subset of that surficial geology map that serves as our hazards mapping footprint. And within that footprint, we choose study sites where we do our more detailed work. And again, we do that in consultation with the community and also to try to capture a range of conditions that we find within our hazards mapping footprint. So our approach is sort of three-stepped. We start with our desk-based work, looking at existing maps and air photos, existing reports in communities, doing that community consultation that I talked about. And then we have our field component, which is always really a lot of fun. So YGS goes out and does the surficial geology mapping. They also do ground penetrating radar. That's the piece that Sarah Laxton does, who presented yesterday. Tony's group does the electrical resistivity work. And then out of the Northern Climate Exchange with our partners at University of Ottawa and Montreal, we do the permafrost coring and borehole drilling aspect of the project. And we've been able to, over the last couple of years, build our capacity at the Yukon Research Centre with our lab to do all of the analysis of our permafrost cores in-house. So that's been a good step forward for us. And then we do all the analysis, as I was talking about, the grain size distribution, the ice and water contents, the permafrost properties, the interpretation of the ERT and the GPR, and integrate that at the end of the project. The other thing that we incorporate as part of our projects are projections of future climate. We use a range of climate projections, a low, a high, and then an intermediate scenario over 3 time steps. And so in that way we capture a range of potential future climate conditions. And then we use permafrost probability models. And this is where I'm going to turn it over to Phil, who's going to describe that in more detail. And then I'll come back again after Tony to wrap it up.
Philip is currently a postdoctoral fellow in the Department of Geology at Queen's University. His research interests focus on the use of modeling in environmental systems at different scales of time and space, and more specifically, in understanding the evolution of land and water landscapes in the past, present, and into the future. And maybe, Phil, you can explain what that actually means.
I was hoping you had an answer to that. All right, so today what we're going to be looking at is some of the work that Bronwyn was really introducing you guys to. And this is part of a greater project that looks at the hazards, and it's just kind of something that kind of got rolled into it, but that we've been working on for some time. So the title of this is looking at permafrost probability modeling and also some modeling that looks at air temperature scenarios and some kind of adjustments to GCM predictions that we were able to make with Bronwyn's group last year as well. So I just want to acknowledge my co-authors, of course, Tony and Graham Pope, who did a lot of the GIS work in the air modeling. So to put this presentation into some context, what we're actually looking at is we're dealing with mountain permafrost, but specifically within discontinuous zones. And I've kind of highlighted the word discontinuous here because in the range of these areas, of course, a lot of the adaptations that we're looking at are in community areas, but we deal with a lot of this in ranging topography, where we have everything from seasonal frost to isolated patches, various types of discontinuous permafrost, and of course up to areas that are continuous and very, very cold as a result of that. Really what I'm looking at, though, in this particular stage is that we've developed models of permafrost probability in the past. And for the most part, what I really want to understand and look at is understanding and characterizing how the spatial morphology of the extent of permafrost in these areas will change as climate changes in these environments. So this really allows us to really look at the idea and assess basically how the loss progresses and how this loss is actually happening over these various areas as an area as a whole on both very large scales and smaller scales as well. So looking at these questions. Also, the second portion of this project, which is kind of, a bit of a change in gears, but you'll see how they link together, looks at the idea of linking air temperatures with permafrost. This has been kind of, alluded to in some of the other projects that we've looked at as well, and we've found some interesting results that we want to present here as well. So that being said, I won't really get into the specifics of how models are derived or anything along these lines. This is a model that was published in 2012, and we worked on this for quite some time. Quite a few of you have probably seen this model before. It's a permafrost probability model at 30 by 30 meters resolution. What you can see from here is logically it reads that the cooler, darker colors represent high probabilities of permafrost, whereas the warmer, redder to yellow colors represent lower probabilities of permafrost. The other thing to keep in mind is that thermometer, which you see there, and that thermometer pretty much shows us where we're looking at. We apply a bunch of climate change scenarios to this particular model, so that thermometer will help you see where we actually are in the scenarios that we're looking at. So the current thing that's interesting to take out of this is our base case scenario, and we see that the Yukon is under this prediction underlaid by about 58% probability of permafrost. So 58% of the territory is underlaid by permafrost. Also, though, what we can do, and this is alluding to the work that Bronwyn spoke about, is that we can extract values from here for our communities. And this is a figure that you will have just seen as well. And we see that you can go into this, and that same resolution of 30 by 30 meters allows us to assess what permafrost conditions are like currently and potentially into the future as well under equilibrium conditions for the communities that we looked at. These are two of the ones that we looked at last year in Burwash and Destruction Bay, and it reads very similar. Of course, the scale is different in here because we've zoomed in quite a bit. So we can explore changes, as we've mentioned, and the primary variable that we look at in this is something called equivalent elevation. And I'm happy to speak about where we derive this model from, or this variable from, that reflects complex topography and differing lapse rates in the Yukon. But for the most part, what we see here is that we want to look at the question is, how is climate change driving the distribution of permafrost in these systems? So by altering this model, by making additions or subtractions to the primary temperature controlling variable in the surface, which is this equivalent elevation term, some of you will be familiar with this, we can effectively simulate these changes across our modeled space. Now, one of the important things about looking at modeling that I hear a lot in the empirical statistical modeling is that people put a lot of stock in absolute results. And in this type of study, what's important to take out of this is that we're not necessarily too hung up on a lot of the absolutes, but where we're really looking at is seeing the relative behavior of these systems, geographically seeing how the loss is affecting different areas, relatively speaking. If we effectively have modeled the system, that's really what we're looking at. So how this is happening over warming sets of conditions. So it's a variety of different scenarios were applied. We applied fixed scenarios through here, fixed rates of change, things like plus or minus 1 degree, plus 2, 3, 4, and 5. And we've also done some smaller versions as well in recent times. So when we apply these to the models, we can basically run these through and see kind of what results in the permafrost extent changes. So this figure here is one that shows us what permafrost conditions may have been like during a 1 degree cooling scenario, so possibly during the Little Ice Age. This is pretty important for some of the work that we're currently proposing to do, which looks at the evolution of these systems and how they evolved in the discontinuous zone, whether or not they evolved from a discontinuous environment or from a continuous environment that has become discontinuous. What we can see here, though, in this particular figure is that permafrost is much more extensive throughout the territory under this minus 1 degree cooling scenario. And this is, of course, for the unglaciated territory. 76% is basically how this has changed. If we go back to the base case scenario, this is kind of what things are like presently, we can see that there is quite a bit of change with just a very small alteration in temperature as a result. We can also warm this up, and this is what it's like under a 0.5 degree temperature increase. We've lost 10% of the permafrost in these areas, and considerably. Where this is really being affected is these areas in the communities, which are generally at lower elevations, and also in the north, where we have very complicated lapse rate patterns, where temperatures can actually increase as you go up mountain below tree line. If we increase that to the full degree, we can see that we've lost 20% of the permafrost from the original. This isn't really a huge change under a scenario base, and it's only about half of what's predicted by the IPCC scenarios by the end of this century. We can then warm it up, and we can see the progressive warming, 24% at 2, then from there at 3, 17, 12, and then finally 9%. So very low amounts are remaining, and permafrost is really only present at the highest places in the areas where they were the coldest temperatures as a result of this at 9%. So looking at this, one thing that comes up is kind of the idea of, how do we've seen the pictures, and visualization is quite important in these studies because a lot of people can look at this and they can get an idea of the drastic changes that are coming as a result of climatic change potentially. But what we see is actually understanding and breaking down how this loss pattern is basically different across the different areas and the different communities that we see. So in particular, what we really want to look at here is understanding this spatial loss, how it occurs, and how these systems will actually evolve geographically in these particular areas. So this is quite actually important, and it kind of alludes to a point that Steve Coquelle brought out yesterday in looking at the susceptibility of areas. We want to know which areas are susceptible to certain behavioral patterns based on what we've seen presently, and this is kind of how we're breaking this down for the most part. And what it appears is that this loss path, with the term that we've termed loss path, and how permafrost, contours, if you want to call them that, basically how they move across the surface, appears to be quite complex. It's different geographically, and it's different in these areas where our lapse rates are different. Now, in the north, our lapse rates are highly inverted because winter is predominantly the dominant season that we see. These are in areas like Dawson, where we see various different behavior as well in places like Whitehorse or in Haines Summit as an example of that. So looking at that, I won't really totally get into this, but what we can see is that we've identified various different types of loss paths that we look at as a result of this. First one, which is the easiest one to understand, and I have graphics, I promise, that make these a little bit easier to understand. But what we see, the first one is called simple unidirectional spatial loss, where we have one pattern above and below tree line that we see the loss path moving up. The second type, termed complex unidirectional spatial loss, implies that we're going up mountain with the lowest probabilities of permafrost moving from the valley bottoms towards the summits themselves. But it's happening according to two different lapse rates, one below tree line and one above tree line. Whereas in bidirectional spatial loss, typically where we'd see in the most continental areas, such as Dawson as an example, we see two different loss fronts moving at two different lapse rates. So what does that really mean? Well, if we look at this picture, which is my stereotypical picture of a mountain here with my tree line there, my best artistic abilities, what we can see here is that the lowest probabilities of permafrost are in the valley bottoms, the highest on the mountain tops well above tree line. Now, if we apply a warming scenario to that, we can see that those low probabilities are basically moving from valley bottom up mountain as a result of this. The loss path moves to higher areas. If we look at the second type, which is complex unidirectional spatial loss, in areas that we will see lapse rates below tree line that are still positive as we go up mountain, it still gets colder, but not nearly at a rate that we would expect, not at negative 6.5 degrees per 1,000 meters, maybe something along the lines of -3 or -2. So we can see that it moves in the same way from valley bottom up mountain, but according to two distinct different lapse rates as a result of this. Now, finally, in the third case, the bidirectional spatial loss, what we can see here, and this is in areas where we have extensive permafrost through the valley bottoms, areas where we have cold air pooling, such as we see in Dawson, in Keno, in areas like this. What we can see here is that when we apply a warming, what happens is that we get the loss path that moves in two different directions. Below tree line, it starts to move down valley, whereas above tree line, it moves up. And it does this at various different rates, depending on the strength or the weakness of the lapse rate in these particular areas. So understanding really the morphology of how these change, well, really means that we're going to be losing permafrost in different areas, in different communities, in different parts of the territory. And this is really assessing how the model's behavior exhibits itself when a climate change is applied. So looking from there, what we're going to do now is we're going to kind of shift gears a little bit. It seems like these two models are not necessarily related, but they are actually when we're looking at some of the things. Now, through an effort last year, actually, what we were able to do was, bring an idea to the forefront with NCE. And doing this, what we did was we applied air temperature modeling scenarios with our knowledge of the lapse rates and the climate that we had in the Yukon. So this is pretty typical, this air temperature modeling. This is, not really a representation of a GCM, but this is the resolution that GCMs operate in. Now, anybody who's been to the Yukon, of course, knows the complex topography in these areas, that temperature varies quite a bit over these 100 kilometer grid cell levels. So kind of the idea behind this that we were looking at was, how are these two related? How is permafrost related to air temperatures in these different scenarios that we looked at? Now, the others were really, at this point, what we've looked at in the modeling is fixed scenarios, that it will uniformly warm up by 1 degree or 2 degrees. Of course, in reality, that's not really likely, but this is kind of the basis that we were looking at. So the challenge really came up last year, which was the idea of building a better climate model, something that we could actually relate to, that wasn't on these 100 kilometer grid cells, or even on the 2 kilometer grid cells, which is what the statistically downscaled data is actually on, making use of all the knowledge that we collected of the lapse rates and the various differences in climate across the area. So with this knowledge and our areas that we know of tree line, what we were able to do was that we could model mean annual air temperature in these particular areas. And this was an adjustment, for the most part, to our model that we had made several years back using Environment Canada data and our own logger data with the knowledge of the lapse rates in these areas. So that being said, this was kind of the model that we had. And when we started, this is our starting point. And what we can see here is that we have a variety of different temperatures across the Yukon. They vary with elevation, but they don't vary necessarily in the ways that you would predict. One of the problems essentially here was that most of the climatic areas, the climatic stations, were located in valley bottoms, and that's where we have a lot of the data. So using this as a template, what we were able to do was essentially overlay the statistically downscaled GCM data onto this, and then get an idea of how these projections could be modified for these areas in the Yukon. And this is what we've done, for the most part, is linking the predictions that are made in the macro sense from the GCMs to our own adjusted more fine-scaled model that we've actually looked at. And this used the statistically downscaled data from SNAP for scenarios A1B, A2, and B1, and I'll show you some of those results in here. And what this really does is it preserves the unique topographic climate predictions in the Yukon that we see. It has knowledge of these lapse rates, which are quite interesting, and they change, as we've mentioned, at treeline as well. So that being said, one of the models that we made was a backcasted model. So what climatic conditions might have looked like between 1950 and 79. We can see here down below the legend, I know it's tough to see, but we can see that there is a mean temperature of negative 4.4 degrees for the entire territory. So this is our current case, and we can see negative 3.47 in this particular case. Now, using these scenarios, what we can do is we can warm these up for 3 different time periods. This is scenario B1 for 2020, and that's to negative 3.05, and then 2050 and 2080. That being said, this is really the most conservative of these estimates. This is the B1 scenario, and we actually have it as well. This is back to the current. We have this for the A2 scenario as well, which is the most aggressive. And we can see that as we warm this up by 2080, well, we're looking at a temperature that's just a fraction below 0 for the entire territory at this particular case. This is the mean, of course. So how do we link these together when we had these 2 data sets? What we looked at was really linking permafrost probability to MAT. One of the great things about this is that we had a lot of data. We had a lot of data that looked at where permafrost was in physical ground checks. And what we saw from this is that we took the modeled results from the model and we linked them to where we saw permafrost and we didn't see permafrost in about 800 pits in the Yukon. And we can see that here, there's a clear change that happens between there, where we have areas that we don't have very high amounts of permafrost, and then all of a sudden it explodes upwards. Now, that being said, we can also plot that on a logistic curve, which looks at basically linking the probability of permafrost with the air temperature itself, and it runs along these areas. So when we do that, one of the things that was interesting that I found about this study when we set out to do it was we tried to identify what we thought would be important air temperature thresholds for permafrost. And one of the ones that stands out is obviously around 0 degrees Celsius. And what we thought might have been safe for areas around, something between -1, -2, even down to -3, well, we found that these areas were not necessarily what we would have considered safe. If we look at where our probabilities of permafrost are at the various air temperatures, what we can see is that they fall on these portions of the curve. So at 100% probability, well, we have to be pretty cold at this particular point, below negative 7.5 degrees Celsius. But what's really interesting is that if you look at the temperatures in a lot of these communities, you can see that they're actually above negative 3.35. This is also, the temperature that Steve Wolf yesterday alluded to as what was said for what you needed to have permafrost. And we're seeing a little bit of a different result in here, but for the most part, this highlights our very, very steep portion of the curve. That if you change temperature by only a little bit in these particular areas, well, it's going to have big reflections in an equilibrium sense in what we see in the permafrost in these particular terrains. So that being said, just some conclusions to really draw from at this particular point is that the areas that are most prone to susceptibility changes in a sense and are prone to these changes in both air temperature and permafrost changes as a result are areas that have surface lapse rates that are very close to zero. And that's because for the most part what's happening here is that we're seeing that they are not elevation dependent in these sense. They're elevation independent, which means that elevation is not necessarily helping them. We see big spatial losses. Also, what we're seeing is that if they display bidirectional spatial loss, that kind of in the most continental areas, like what we see in Dawson, they're very susceptible to these changes. And that if they happen to fall between this range of about negative 2.5 and negative 4.25, well, these are really the areas that we need to pay attention to. And these are the areas that are also in the communities. These are about the average air temperatures that we see, where we start to see problems as a result of this. So really what we're trying to do now is also use this modeling with other studies and collaborations to basically put it into this and see what other types of environmental modeling we can look at. That being said, thank you very much. And
we have time for one question. If you don't have any questions right now, there'll be an opportunity at the end of this session. But one question, yeah.
I got one question. Thanks, Phil. How does time come into your modeling? Because I imagine it's a big difference whether we warm 1 degree in 10 years and we're warming it in 100 years. So how does time is incorporated in your model? Or if you could
well, the short answer to that is that it's not. And for the most part, these models are not really set up to look at those types of changes. These are under equilibrium situations, but so that's very important to actually bring out to the forefront.
Okay, thanks.
Okay.
Thank you, Philip. Our next speaker is Antoni or Tony Lewkowitz. You may remember Tony spoke late yesterday afternoon. Tony is a professor in the Department of Geology at the University of Ottawa. He has been a permafrost researcher for more than 35 years, working in the Canadian High Arctic, Mackenzie Valley in the Delta, the Yukon, Labrador, Northern Norway, and the Antarctic. This morning he'll be talking to us about the use of electrical resistivity methods to investigate permafrost sites.
So thank you very much. I'm really going to focus on this presentation using ERT as a tool, and it's proven to be a very important tool in terms of the hazard mapping, but I'd like to speak more broadly and suggest that it's a tool that we need now to use in any investigation, almost any investigation of sites or distribution of permafrost in the discontinuous zone. And again, I will emphasize the discontinuous zone, but as we've seen for much of the Yukon, with the exception of Old Crow, most of the communities are in the discontinuous permafrost zone. And I'd like to just acknowledge my students who've helped on this presentation, developing the data over the years, Christina Michelli, Maxime Duguay, and Alex Bevington, who's in the audience. So first of all, what is ERT? Alex apparently managed to get one of the grade school classes at Dawson School this past about a month ago to chant electrical resistivity tomography over and over again, so it apparently has a certain ring to it and a rhythm to it. ERT, for short, is a geophysical technique in which we pass electrical current into the ground and measure what comes back in terms of the voltage. And we do this with a line of electrodes that's known as an array. And basically, in the middle of those electrodes is a box, which is this instrument here, in this particular case, which is a complicated switch and basically a multimeter stuck together with a computer interface. And so we have the box in the middle, we use a car battery to provide the power, and then there is a line of cables going out on either side that's attached to electrodes. This is the basic principle. If you have 4 electrodes here in a row, we have a whole range of them, but I'm just focusing on these 4, and you apply a current to these outer electrodes, the current will pass through the ground in a particular path. This is idealized, and then we can measure the voltage back between these 2 electrodes between the 2. Now, in the context of permafrost, if we have these electrodes relatively close together, the current path will be through the active layer, and just through the active layer. So we end up getting a measurement here of the voltage that relates to the electrical energy passing through what is a low resistivity. In other words, it conducts well. Resistivity is the opposite of conductance. So a low resistivity environment, because the water in the active layer is unfrozen and it's good at passing the electrical current. On the other hand, if we pass them through these 2 electrodes, we apply that current, and then we measure back through the voltage across these 2, then the electrical path will be deeper. It will go through both the active layer with a low resistivity and into the permafrost, which has a higher resistivity because the ice is a poor conductor. It has a high resistance. So if we do that, we can basically figure out what's happening from a combination of, at this point, we get everything through the active layer. At this point, we get both the active layer and the permafrost. And we can disentangle that using software, those 2 values, because we always just get an average value. But if you have 3 people in a row, one is taller, one is shorter, and the third person is shortest, and you measure the average of, you first of all measure the tall guy, then you measure the average of the first 2, and you measure the average of all 3, you can actually disentangle backwards what their heights were, and this is the same principle here. We use an ABEM instrument. Please note I have no shares in ABEM. It's a Swedish company, but it happens to make an instrument that's particularly easy to use, and I should add that I am not a geophysicist. I'm trained as a geographer, so I'm a user of this equipment, and I think that's a critical point that I want to put across today, is that I believe this has moved beyond the research and into a user environment, and that's really why I think it's a useful tool for us. So the results of that survey appear as on the screen. You may just be able to see the colors here. In this case, red is always high because they don't really work with permafrost, but you'll see in the later sections I show you that I've reversed the color scheme so that the blue is high and red is low, because in general the red here represents a high resistivity, which is permafrost, and the blue represents a low resistivity in this particular diagram, which is non-permafrost. When you finish the survey, you offload the data on a USB key, and then you can put it into a computer to do the disentanglement part that I mentioned earlier. So is this new? The answer is not really. It's been around, in fact, for at least 20 or 30 years, but in the old days, electrical resistivity work was done at a single site. So it gave you a number or a change in depth that was basically like having a single borehole. The difference is that now we've got equipment and software that allow us to look at a 2-dimensional section. And I think it's time for us to start using this more broadly as a very cost-efficient way for us to find out what's happening across the terrain rather than just knowing what's happening at a single site in the terrain where we get a borehole. So how do you undertake an ERT survey? Well, first of all, choose your site. And in this case, this is a thaw slump actually on the Takini River. We set the midpoint here, and we run our cables down and we run our cables up. We move the terameter and the car battery to the middle. You push an electrode, which can be, in fact, if you really want to go light, you can use a 12-inch nail, but we have stainless steel electrodes that we use. You push them into the ground, you attach them with jumper cables, and you start the survey. The survey itself, depending on how you, from the point when you push the button on the terameter and it starts putting electrical energy into the ground, may take half an hour or 45 minutes. It may take you an hour to set up, depending on the bush that you're going through. The depth that you get in terms of the survey as a result depends on the length of your electrodes and their spacing. So to give you an idea, we use a particular array. It's just a layout, a Venner array, where for an 80-meter array, we'll get 12 meters depth in the middle. For 160 meters, we get 25 meters. And if we're able to set up a 400-meter array with 5-meter spacing on the electrodes, we can see to a depth of 60 meters, which is, of course, putting us into the point where we might have quite thick permafrost. It's important to note that the bigger the depth, the less the resolution. So we don't see as much detail when we're using a long array as a short one. And I can tell you 400 meters is a long distance. There are many sites where you can't set up 400 meters without having lakes or ponds or rivers in the way. And certainly within a community, it's pretty difficult to set out 400 meters without people running over your cables. And each cable costs $5,000, so you really don't want that to happen. So what are the advantages of this? This is the very first site I actually did, which is the RCMP post at Beaver Creek, which just happened by coincidence. And to my surprise, this playing field in the foreground still had permafrost beneath it. It adds a second dimension to frozen ground conditions compared to a single borehole. In fact, you can even do three-dimensional images if you do a series of two-dimensional sections, one next to the other. It's non-invasive. Nobody will worry about it. They may think that they should be worried about the electrical energy, but it comes from a car battery. It's tiny, tiny amounts of energy that go into the ground. You remove everything at the end, so it's non-invasive. You can do a survey even beneath a raised building. You can do it even in water, which is sort of a surprise, but you can. Of course, somebody has to wade into the water to put the electrodes in. That was Alex. A single person, I've done surveys just entirely by myself. You can do them in about half a day, but if you have more people, you can do it faster. And you can carry all the equipment, this equipment anyway, in about 4-person loads. There are other manufacturers. It's inexpensive to undertake a survey because it's basically time once you've paid for the equipment. And the equipment is about $30,000 to $50,000. So there's a serious investment at the beginning, but after that, it's cheap. And I think it's a lot easier to learn than GPR. So GPR, if you saw some of the diagrams that Sarah showed us, maybe somebody else showed us yesterday, they require some serious interpretation. I think what I want to show you is that it's much easier to interpret ERT values. So now I'm going to show you just some examples. First of all, just to indicate that it's repeatable. This is a site that we have. It's not even in the territory, so I shouldn't be showing it here, but it's near Fort St. John in northern British Columbia at milepost 341 on the Alaska Highway. Not really much evidence of permafrost when you look at this, but there is thin permafrost present. I'm showing this as resistivity blocks, model blocks, what the actual, so it kind of gives you the idea of the resolution. And on the left here, we have a scale where each division is 2 meters, and this is an 80-meter survey. And so the question here is, what is the boundary between permafrost and non-permafrost? And it's around about 300 ohm meters. So this is a block of permafrost. Here's another block of permafrost, and everything else is unfrozen. Now, that's in August 2010. And then we redid the survey in August 2012. And then we redid it again in August 2013. So we've got the same time of year. And what I actually see is that permafrost is probably breaking down in this location here. If you can just keep your eye on that point, you'll see that we're going to yellow, and then we're going to brown, which means the resistivity is dropping here, and we're actually starting to see probably permafrost degrade at this site. Now to look at, in terms of the hazard mapping we've done, I will look at a series of sites. This is at Burwash Landing in Destruction Bay. Here we have an area where we had an undeveloped lot, a fire-smart zone, and we're basically seeing an active layer that runs all the way across here. Perhaps, again, just to give you an idea of scale, this one is 25 meters deep. 5 meters then is one of these divisions over 160-meter length here. The permafrost is obviously visible. Is this the base of permafrost? Possibly. It's down at a depth of about 15 meters. Again, you know, ERT doesn't tell you everything, so it may or may not be the base of permafrost. If we had a borehole here that went right through, we'd be able to tell. But certainly we have relatively thick permafrost all the way across here. Where we start to see differences is when we have surface disturbance. So here is a fire-smart zone followed by a fire break. And now we can see that we've got thaw taking place here to a depth of about 8 meters at the deepest point. We have the effect of a gravel road, obviously also thawed beneath, and then here we get just to the very end of the survey, we have forest again. Again, this is 160 meters and about 25 meters depth in the middle. So permafrost is fairly thick at Burwash Landing. And here a proposed site in the Copper Joe subdivision. Here we've got the effect of the forest fire of 1999. And so in this part, we can see that we have about 7 meters of talc, so thawed zone, overlying permafrost. Permafrost, these are all on the same scale, but notice how this is a lighter color, but still almost certainly permafrost. And that probably means it's warmer. So the water, there's more unfrozen water in the soil, and as a result, that's starting to conduct energy. And as a consequence, it's coming out as less blue than in the other sites. So we can definitely see that we've got unfrozen materials, and these are backed up by a number of boreholes that were done by the Université de Montréal team, in which they either didn't reach the permafrost or did reach the permafrost, but in many cases just ended up saying, well, we got to 2 meters and it was all unfrozen, and we didn't know what the conditions were like underneath, but the ERT shows what was happening underneath. So here's another series of sites, just the ones done recently at Dawson. Now, this profile here is 60 meters deep and 400 meters long, and it's an undisturbed zone in West Dawson. And what you can see is basically there's permafrost all the way to the base. It's just possible that we're starting to see the bottom of the permafrost here at 60 meters. There's the effect of a little stream just causing the permafrost temperatures to be higher, but there's no talcs present. And the Yukon River is just right here. In the Dawson School, which Alex did with the school kids, we have a very different situation. This is only an 80-meter section, so we're only looking to about 12 meters of depth. And here you can see that, again, the same scale as the one above. We've still got permafrost down beneath this site, but there's a significant talc overlying it, 5 to 6 meters deep across the area. So without drilling, we can tell you what the conditions are at this site. And here in the Klondike Valley, another site that we went to, there's a cleared field, which is shown here on the left, and then there is this area that's obviously where the material was just bulldozed, and that's right here. And then we have spruce forest, and then there was a deciduous forest over on the right-hand side. It's a long section, but it's only 25 meters deep. And you can again see that the cleared section, we have a talc present to a depth of 5 meters, and what's really neat is just here, you can see everything is thawing even faster. And I interpret that as being because we get a snowbank that builds up there in the wintertime. From the wind blowing across the cleared area, the snow's going to accumulate right at the edge where all that material has been bunched, and it's showing up on the profile. This area is large, deciduous trees, no organic mat, and it seems to be unfrozen. So in case you now think that you will need to go out and buy ERT equipment, I must put in the interest of honesty, say that ERT is not always a perfect technique, just as no technique is perfect. It gives you measurements of electrical resistivity. It's up to you to do the interpretation. And like all geophysical techniques, you need some kind of calibration. That can be as simple as doing frost probing, seeing, yes, there is permafrost present at this site. I can feel a frost table. But of course, the areas we're most interested in are where we can't feel a frost table, so we need to be able to calibrate in some fashion, preferably with boreholes and borehole temperature measurements. The contrasts that we're looking for to try and explain what's going on are best where we have cold permafrost. But the places we're most interested in are places where we have a lot of unfrozen moisture, and so the contrast becomes less at that point because the electrical energy passes quite well through the unfrozen moisture too. And once we have bedrock, then it starts to be much harder to say what's going on unless there's water in the bedrock and it's fractured and there's ice present. And finally, I haven't actually done any saline permafrost sites, but I've seen some done in Alaska where the resistivities are very low, which would say, oh, no frozen ground here, but that's because the salt is conducting the energy quite well and there is in fact frozen permafrost. So I just want to give you a couple of examples of more difficult, challenging sites. Here's Mount McIntyre, which is one of the mountains overlooking Whitehorse at a height of about 1,600 meters. And a long profile that we did here where the colors would suggest, oh, well, there's definitely permafrost present, but there's something funny going on in this area and in this area. And we weren't sure. This is bedrock. It was very difficult to judge whether there really was permafrost present. As it happens, there is. We drilled a borehole, and it's about -2. So all of this is definitely permafrost. This is probably the effect of groundwater movement at this site, but again, we would need further investigations to be sure. And without the borehole, we could not be certain that permafrost was present. This is Burwash Landing, a wind generator site, and here again, you can see really quite complicated relationships. This might be bedrock on the left-hand side, or it may be even an artifact. These are definitely permafrost areas running across, but you can see they look potentially discontinuous. And these two boreholes both showed permafrost. This one is easy to explain. It's coming right into an area that we would judge to be permafrost. This one is right into a red area, which is a talc or an unfrozen zone. However, it was done 10 meters or 15 meters off the actual line of the ERT. So what's happened in this case is not only do we have discontinuous patches going this way, we have them going at right angles into the screen too. So it's important that when you do a borehole, it's right in the place that you want to look at, because otherwise you may not be able to explain what's going on. On the other hand, if I had to advise where to put your wind generator, put it there, and don't put it in any of these sites which actually have ice-rich materials in them. So to conclude, this technique, I think, has proven to be a very valuable one, in fact, one of our primary sources of information for the hazards mapping project that Bronwyn was described. We can evaluate conditions much better and to much greater depth than solely by the drilling that was undertaken. Those two-dimensional profiles show what's happening laterally, which is exactly what we expect in discontinuous permafrost. Things change. And I think that if you were to investigate a single site, a building that has problems, or a place that you want to build, it's now essential that we start to use ERT if we think there may be lateral differences in frozen ground conditions. And as I suggested here, you can even do this underneath a building. Thank you very much.
Any questions for Tony? One at the back.
Question from Stuart Nash at Associated Engineers. Have the investigations been done at the same location in the winter and summer? How do the depths compare over the season?
The answer is that we did indeed, at the site that I showed you, the sites that we have along the Alaska Highway, we did a whole year of seasonal measurements with an array that was arrays that are fixed in the ground. And what we see is that, indeed, just what you'd expect, that we get a high resistivity layer that develops in the wintertime due to ground freezing that then connects onto the permafrost. The interesting thing is that because you've got a high resistivity layer that's over a low resistivity layer, when you come to do the interpretations, it can suggest that there is some changes in areas that we interpret as being non-permafrost. So what we suggest is that the best way to do this is to always do it at the same time of the year, which is in the summertime when you have a low resistivity layer, then a high resistivity layer, then another low resistivity layer when you're looking through thin permafrost. And perhaps what I will do now is hand it back to Bronwyn to close things off, and then if there are any more questions, Mr. Chair, perhaps they can come afterwards.
I have a question.
Oh, okay.
I've been listening with great interest to the various presentations dealing with atmospheric effects on permafrost and also boreholes. Now, is there any research being done about the radiated heat from the Earth's core, which is in fact a reality? Is there any research being done under the permafrost?
Well, when we measure ground temperatures, you can always interpret what the geothermal heat flow is. If you have a deep borehole, it's possible to convert those values into geothermal heat. But I would have to disagree with you that the primary cause of climate change is from the radiation from the sun and its entrapment by changes in the greenhouse gases in the atmosphere. I would not agree with you at all that what we're seeing in terms of permafrost is due to a change in heat flow from the center of the Earth.
Yes, and I wouldn't agree with you at all either.
Fair enough.
Isn't that the wonders of science? Bronwyn?
So, Marin, can you pull up? I'm partway through a presentation that's minimized there. If you could pull that up, that'd be great. I want to come back and talk about how we integrate the work that Phil and Tony have just described in our hazards mapping projects. I can just scroll us forward. Okay. So Phil and Tony have just described two pieces of the project. We start, so yeah, I want to talk about how we're integrating all of those pieces now and converting the knowledge that we have to our hazards map. So we start with our surficial geology map, and this is all examples of data that we've collected at the Copper Joe subdivision, which is in the vicinity of Burwash Landing. So we start with our surficial geology map from the region that we're working in, and we use the polygons that are outlined on the surficial geology map as the polygons that we rank in our final hazards classification. So this map becomes really important both in telling us about the landscape that we're working in and in the basis of our hazards classification. And then we integrate the resistivity profiles that Tony just described and the ground penetrating radar to really give us a good idea about what's happening laterally and also with depth at the study sites that we're working in. And as Tony described really well, it's important to do some ground truthing work. So we're also doing boreholes and collecting cores. So this is an example of some of the cores that we collected from the Copper Joe area to verify some of what Tony sees in the ERT profiles, and also to look at things like thaw settlement and consolidation potential at the sites that we're working in. We take all the information that we've gathered and we do a qualitative assessment of hazards at the sites that we're working in. We have weighed the value of doing a really quantitative based hazards assignment, so ranking hazards, assigning values to the different components that we're working with and using those to develop the hazards classification versus the qualitative approach that we're doing here. One of the things that I want to emphasize is that the hazards mapping projects that we're doing last a year or two. So they're pretty short, and we're trying to collect as much data as we can in that time, but we haven't been able yet to collect enough data to do a really quantitative approach. We also, when we're doing a qualitative approach, have the advantage of applying what we know and what we hear from communities about the landscape that we're working in across our map area. So we sit around a table and we discuss what we found at all the sites and what that means across the map area and assign our hazards rankings to each of the polygons on the surficial geology map. We number the polygons and we describe in a report what hazards are associated with each polygon so that people who are using the map understand what's in the back, what's in behind. This is the map from Burwash and Destruction Bay, and we put it up in the communities when we finished the project, and we said, green areas are pretty safe, red areas are areas you probably want to stay away from. And they said, so where's the green? How is this useful to us? And sure enough, there is very complicated permafrost in this area. It's still useful to the community because they can make decisions around the ways that they develop and the sites they choose for future projects. So Tony alluded to this wind farm site. Kluwani First Nation is interested in reducing its reliance on diesel, which is what provides most of the power for the community. So they're investigating the potential of setting up a wind farm on Kluwani Lake. And so this is the site where they're proposing to do that, and they're working on setting up a wind monitor to see the feasibility of doing this kind of project. And it's red. So we have ranked that as having high risk of hazards, primarily associated with permafrost. Tony showed you the ERT line from this site. That's still useful information for the community because they can make decisions around how they build and what they build. So how they engineer the tower when they do the construction so that it's as safe as possible, so that it suffers the least amount of degradation as possible should the permafrost at this site thaw. So these are the kinds of decisions or information that we'd like communities and planners and engineers to pull from these maps as a first pass sort of baseline information gathering tool. And just to head off a question that I had last time I put this up, no, we did not design our map area to look like a corpse. That was not part of the plan. We've done projects in other communities, and I just want to quickly put up an example of the classification system that we did for Mayo. So we came up with a slightly different classification scheme for them because they have a different type of landscape. So they have lots of nice green areas, a good area where they're considering a new subdivision. So we're really tailoring these maps to each community and reflecting what the communities are saying to us about what's happening in their landscapes. And again, we're working in Dawson, Faro, and Ross River, so you'll see those results coming out. All of the work that we've done is available on our website, so those reports and maps can be pulled off there. The last thing that I want to talk about is how we're bringing these results back to the communities that we're working in and how we're transmitting the information that we've gathered to the decision makers that can use it. We don't want to produce these maps and reports and have them sit on a shelf. We want to have them front of mind for people when they're in a situation where the information that we've gathered here can be of use to them. So one component of that is bringing them right back to the communities that we did the work in. And what we did in Burwash was a bingo night, and that was a lot of fun. We had about 60 people come out, which is a really good turnout in a small community. So we had a dinner, we talked about the project that we did while folks were eating, and then we played bingo. It was a good way to celebrate the end of the project and to get lots of people out and hearing what we were working on. We invite decision makers and end users to meetings and tell them what we've done and how they can use these maps. One of the things that we're thinking about for the maps that we've just recently completed is to turn them into posters and put them in public places. So, for example, in Burwash and the post office. Everybody goes to the post office, people stand in line there. Having the maps in public places, we hope, will keep them front of mind. And then doing things like formal thank yous in community newsletters or on community Facebook pages or websites. The other way that we've been working to get our map layers in the hands of decision makers is to upload them onto the Geomatics Yukon website, which is the data warehouse for GIS-based and geomatics-based information in Yukon. So people can come to that website, look for information around their communities, pull down the maps, and use them as layers in whatever geomatics system they're working in. We've held workshops with potential end users to ask them, how do you want us to communicate these results to you? We're working on doing a lay report, a Hazards 101 kind of report. And then the other thing that we've done is develop a comic, a hazards mapping comic. So I'm going to have copies on the desk, on the table at the back for you. But we made this as an accessible way of communicating what it means to do a hazards mapping project to a community and why it's important. So we have an illustration of the wind turbine site, and then some talk about how communities can use the maps. And if you've ever wondered what Antoni looks like as a comic character, there he is. So we'll have those in the back if you'd like to take copies with you. And I do really want to acknowledge the partners, first of all, the communities and First Nations that we work with that support our work, and then the partners that contribute to the project. We are really trying to build our permafrost capabilities at the Northern Climate Exchange, but we can't do this work without partners like Antoni and Phil. So, and of course the funding that comes for these projects. I think it's really important that we come to do the projects in communities with all the funding that we need to do the projects. So it really makes it easy for communities to buy into the work that we're doing. That's it.
We have approximately 5 minutes before the break. If anybody's got any questions for Bronwyn or any of the other presenters that you've heard this morning.
Yes, this has been very, very interesting. And I'd like to, I guess, bring up the previous question of how time enters into this, because all of your hazards maps really are snapshots, right? But when we develop infrastructure in any particular location, we want to design it for a 30 to 50 year lifetime. When will we be able to build a model that is able to forecast changes in permafrost at any particular site, linking all of the data that we have as far as geotechnical, permafrost conditions, air temperatures, climate change, and so on.
We try to do that in the reports that we produce, maybe not in a way that's as integrated as you're talking about, and I certainly see the value of that. We do include in our reports the projections of climate and the permafrost probability models that Phil does. So, and we also keep those in mind as we're doing our hazards classification. So if we're thinking about an area that's, you know, has a mean annual air temperature of -2, -3, and it has lots of really ice-rich permafrost, we're going to be more apt to classify that as high risk, knowing when we see climate projections showing, you know, increases in air temperature and knowing that those will result in subsequent increases in ground temperature. So that's included in the projects that we're doing. Yeah, that's the way that I can answer that. I don't know if that fully answers your question.
Bronwyn, Don Haley, consulting engineer. Hazard mapping is great, and I think the work that you're doing is very timely. Having 40 years with EVA working in Yukon, it's been our experience, myself and my colleague Richard here, that there's always surprises that we run into, even though we do the surficial geology, the hazard mapping, etc. We find that when we actually get into the field and open something up, there are big surprises. And a big part of that goes to the fact that there are buried hazards, deep buried hazards, down 30, 40, maybe 50 meters into the ground. We're finding substantial ground ice left over. And if you look at the work of Dwayne Froese at University of Alberta, for example, he is saying that in the Dawson area, the non-glaciated area, there's permafrost and ground ice that may be hundreds of thousands of years old. At least that's his thesis, and from work we've done in the Carmacks area, we've run into that situation as well. And when you look at Ross River, for example, where we've been working for 40 some odd years, the real hazard is down 30 plus meters in the ground in sediments that you can't see from the surface, and you wouldn't expect necessarily from a straight surficial geology mapping. So I guess my question now is there any part of your program that deals with collecting real data on some of these potential deep hazards that I'm speaking about, and ground temperatures and sampling to substantial depth to try and understand what the glacial history has been?
Not to the extent that you're speaking of. We do instrument some of the boreholes that we drill with thermistor cables to measure ground temperature. We don't drill as deep as you're referring to. So what we say, basically the answer is no, but what we say when we bring these maps and projects back to communities is this is the first pass, and any work that happens, you know, any building still needs site-specific geotech work related to, you know, deeper hazards. This is, we've constrained the hazards that we're looking at. There are others that we don't incorporate here because we don't have the capacity to do that. This is a broad first pass, and those kinds of investigations are still warranted on a site-specific scale for sure. Yeah.
I have a question for Philip from Ainsley Ogden. How does your model address temperature inversions common in the Yukon?
So for the most part, to look at the temperature inversions is that through a variety of mechanisms, we've classified various areas as having inversions or gentle lapse rates, if you want to call it that. And it's really been set up by a lot of logger data in these areas, in a lot of the places that we worked in. So how it classifies it is by using a variable called equivalent elevation, as I mentioned, but I didn't really explain fully. And this is the primary temperature controlling variable that looks at the distribution of permafrost. So what it does is it's a topographic transformation that basically changes the elevation and the topography so that the highest points are basically reflected by the coldest temperatures. So in essence, the valley bottoms in Dawson are equivalent to the peaks above tree line in a sense. And that's really how it incorporates this into the model. So it linearizes that variable in a sense so that we can predict it in the same way that this has been predicted in other places. In other areas where we don't see inversions but we see gentle lapse rates, it basically adjusts that topography accordingly using that particular transformation.